Good morning to one and all present here. We'll be starting the stream, we'll be starting the session around 11:05. So please wait. Please wait for 2 more minutes. We'll be starting the session by 11:05. let's start with the session. So, good morning to one and all present here. I am Nitesh from IETE ISF, and I would proudly like to welcome you all to the first session of AccessDenied'21 on the topic IoT and Robotics. The Internet of Things refers to a system of interrelated, internet connected objects that are able to collect and transfer data over a wireless network without human intervention. Robotics is the intersection of science, engineering, and technology that produces machines called robots that substitute for human actions. To put it simply, it's the technology that brings nuts and bolts to life. When these two technologies are combined together, it paves endless possibilities for various applications. To educate us more about this transformative field, I would like to take the honor of welcoming Mr. Dhaval Gujar, our eminent speaker for today's session. Mr. Dhaval Gujar is a computer engineer graduate from PICT, working at Espressif Systems for the past year in the field of AIoT. Sir is a tech enthusiast and routinely delivers talks on upcoming technologies. Sir's research works in fields such as AI, information security, and blockchain has been published in prestigious journals and conferences like ACM and IEEE. With great pleasure, I invite Mr. Dhaval Gujar to take up on the session.
And we go ahead.
Yeah, sir, you can go ahead.
All right. So I hope my slide is visible to everyone. Slides? No issue?
Yes, sir. Yes, it's visible. You can go ahead.
Yeah. Thank you for the intro. So hi, everyone. I'm Dhaval, and I'm here to talk about IoT and robotics. Currently, I'm working at Espressif Systems as an associate engineer. So let's talk about IoT first. A quick introduction to IoT and things around that domain. So it's basically an umbrella term which defines all of these internet-connected things that come with sensors. They have the software and the hardware to be able to collect and transfer data over a network. Pretty much any physical object, if it can be connected to the internet, you can call it an Internet of Things. Not necessarily everything should be connected to the internet, but that's where we are today. Now, this has become possible with increasingly cheaper chips. I want to elaborate on this point a little bit. So previously, internet-connected devices only ever meant computers. Then slowly, as the cost for computers and compute chips started reducing, we could get more and more of these smaller chips, which were internet-enabled. And now they're at a price point where they can be put into any physical object and not blow up the cost of that. For example, a normal bulb, which you could buy, would be costing you around 50 rupees. But with an IoT-enabled chip inside it, it would not exceed 100 or 150, 200 rupees. So basically, we are now at a price point in chipsets that enabling them to be internet-connected things is not that difficult anymore. So there are three main components to IoT: devices, networks, and data. I will elaborate on this in the next slide. So keep these three things in mind: devices, networks, and data. So if you look at a layered stack, now layering is a very common thing in computer science. You will observe it everywhere, from networks to softwares. Everything appears in the format of layers. So if you look at IoT layers, then you will typically find these three: devices at the bottom, networks in the middle, and data at the top. Now, how this works in the real world is that you have got a perception layer, which is where you have actual sensors which are getting data from the real world. This is sent via the network layer to the application layer, where the actual data is ingested and then used. So you will now find IoT devices in markets like consumer homes, where you get all of these smart bulbs, smart devices, smart speakers, etc. All of these internet-enabled devices. You will find them in medical field, where you have got hospitals which have got sensors connected to the patients, which are monitoring their blood oxygen or glucose, so on and so forth. Industrial IoT. So IIoT is a very common and growing field, which you will see in smart factories, etc., wherein all of these machines which are working, they have these sensors attached to them, which allow you to do something called predictive maintenance, which is much before the machine actually needs to be maintained. By the time you figure it out, it's generally too late. But with IoT, you can have very minute level diagnostics on how well is the machine doing, how much sound is coming in, etc. And internet connectivity also allows these factories to become remotely accessible. So let's say someone's headquarters are in India, the factories are in China or somewhere else, and they can get all of the data from the factories directly on their dashboards. And this is also fairly common in smart city projects now, where we have smart lighting, which can be turned on and off based on various factors like the light intensity on that day, etc., and agriculture. So precision agriculture is an upcoming field which is heavily enabled by IoT. So in precision agriculture, what typically happens is you want to have the exact amount of moisture content in the soil at all times, and you can maintain that by use of IoT, where you have a sensor placed there and an actual water drip. And when the sensor detects that the water level has gone down, it can start the dripper automatically. So such interfaces are enabled with IoT. So why is this relevant to us? The field of IoT has enabled opportunities in almost every domain that you can think of. Now, allow me to explain this. Now, let's think of any kind of a smart IoT device. It will have many, many layers which go into the internal structure of it. The device itself. So you have got the device hardware. Now, the device hardware will include the chip itself. So there is chip design which you come in. Then there will be software running on that chip, which is typically an RTOS-like environment, wherein you have microcontrollers or something similar, which are doing the actual computation. Other than that, you have got sensors on the device. So there is sensor design. And there is also a design of the actual device itself, which is the housing of that particular device. So if you think of a light bulb, then you have got the outer housing and the internal chipset, which forms the device aspect of it. On the network side, now networks are pretty interesting, and there's a lot happening in that field. So there is hardware, which is your Wi-Fi antenna, there is Bluetooth antennae, there is software. Now, when I say network software, it has got two layers. One has got a low-level driver, which is the actual Wi-Fi code. So let's say Wi-Fi is the 802.11 IEEE spec. So the implementation of that on actual hardware. So there is that lower level layer which you have. And on top of that, you have got an abstraction layer, which allows your application layer to communicate with the lowermost drivers. So this slightly middleware-ish part is also a part of the network software. Then you have got algorithms. So algorithms are very, very important to networking, and especially on devices which are memory constrained and which have got requirements such as low latency, etc. You have to be very, very careful in how optimized these algorithms are. Else, you're going to end up in slow networking on these devices, data not going out as quickly, or there's going to be bloating because the buffers are too small, etc. Many, many issues exist. So that's an interesting field. On the application side, you get a lot of opportunities. So you've got web backend. Now, of course, you cannot separate the internet out of IoT completely. So there's always going to be a web backend that is going to exist. That is for the IoT device to communicate with the web backend. Now, this web backend may be RESTful, it might be MQTT based. So there are many, many ways in which you can design backends and many languages in which you can design backends today. And there is web frontend. So frontend technology, you will find it in web applications, which are typically browser accessible ways of controlling IoT devices. Or you can have dashboards for multiple IoT devices, because IoT devices are typically deployed in groups at times. Let's say you have got an entire field, an agricultural field, and you've got devices deployed. So how do I see how all of my devices are doing at once? That needs a web front end. Then you've got the cloud. Now, cloud has become one of the most important tenets of IoT, because the way in which IoT works is that the device always needs to communicate with the internet. We're slowly trying to change that, which we'll talk about in the later slides. But the overall right now is that the cloud is almost an inseparable component from the IoT infrastructure. And cloud is an exciting space. There are a lot of players which are coming out with IoT products. AWS has got AWS IoT, Azure IoT. There is GCP coming out with IoT products. So almost every cloud player wants to be in on the IoT game, and it's a huge space. So if you're interested in cloud computing, then there is always work in the IoT field. Then there is databases. So with IoT, you have sensors on the devices, right? And these sensors typically sample the data at a very, very high rate. And so you get a lot of data. Now, this is not very similar to how normal data is generated, wherein you might get data every time someone likes a post or every time someone comments. Here, the sensor is going to sample the data no matter what. So you're going to get what is called a time series like data, which is at every n seconds, you're going to get a data which is sampled from the sensor. And this data is going to be then sent over to the cloud. Now, that means you're going to have a lot of data coming in a very short amount of time. Now, there is obviously a field named big data around this. And the point here is that databases have to be very, very robust in order to handle such requirements. So now we have got real-time databases which do these time series kind of products, which Amazon and other companies have started to come out with. Then there is API. So we talked about how there is going to be a web backend to the IoT aspect. And one of the things which is fairly common in the backend infrastructure is an API. But APIs are not as simple as people imagine them to be. They have to be designed in such a way that they are extendable. You need to be able to allow people to build apps on top of your APIs. So for example, if I make an IoT product, then other people might want to control this IoT product using their own devices, their own app, their own infrastructure, whatever it may be. But that means that my API design needs to be extremely specific and needs to allow proper access. Another part of API design is authorization. So how do I ensure that the people who are trying to control this IoT device are the intended users? Now, security and IoT has been a mixed bag of things which we'll talk about subsequently. But the thing is that API design is central to creating good IoT products. Then there's mobile apps. So this is almost a no-brainer, because when you have an IoT device, you are most likely to control it with a smartphone or an app. And this obviously currently has Android apps, iOS apps. You have got web apps which are running on both of them. You've got these Flutter or React native type applications. So there is a lot of work in the mobile app development field for IoT. There is UI UX. So of course, the apps and the web frontend that we talked about, both of these are consumer-facing products. So IoT essentially is not always B2B; it's B2C. So that is business to business and business to consumer. So in B2C products, you have to be very careful with how your UI UX is, because if the consumer does not like your product, you're not going to sell a lot of them. So it's again a central part, UI UX. There is testing and DevOps. So we'll talk about the market share of IoT products and how many are being deployed. The overall is that there are so many products which are being deployed right now as we speak, that testing all of these products is an extremely difficult task, because you see, smartphones are much higher end products, and they've got microprocessors which are smart enough to maybe detect their own issues and tell the companies what's going wrong with them. The users are able to submit bug reports. With IoT devices, you don't get that much of leverage. So what ends up happening is that you have got devices which are made and then deployed in the field, and now you're directly going to get reports of it if it has been programmed that way. If not, then you're pretty much in the blind. So testing these IoT devices before they go out is very, very difficult. Now coming to DevOps. So DevOps is a new and upcoming field. And a lot of companies do have pipelines for DevOps internally. And the reason is that software changes very rapidly these days, and keeping all of that together and allowing changes to happen, etc., requires DevOps. So no matter what software product you're building, you're going to need a DevOps team. So this is a very big application landscape for people to take up IoT. Then there is data. Now, probably you were guessing that there's going to be some AI ML stuff in this talk, and there will be in almost all of the talks that you will listen to. And the point is that with IoT devices, we talked about how there's going to be a lot of data, and wherever there is a lot of data, there is always going to be analytics based on it. And this is central to the whole idea of IoT, because you wanted to place all these devices in the field, and that the reason you were doing that was to get data. But raw data is of no use to any company. And on top of that, you have to write an analytics layer. So this is going to ingest all of your data and then it's going to give you some kind of analytics based on this. Now, in case of IoT, this has been useful more in the agricultural and the medical fields. Consumer level, of course, the data is anonymized to some extent, and the amount of collection that you can do from that is limited. However, the idea of using IoT as data sources and building on top of it is going to remain an important aspect of IoT. AI and ML prediction models. So as we talked about these smart factories and predictive maintenance, so we'll keep these IoT devices with sensors near the machines, and based on the kind of sound that they're producing, the kind of vibrations that are happening, based on that we can have predictive models which give you a timeline as to when the device needs to be repaired, that particular machine. And that gives that saves a huge amount of money to these industrial companies. And so this is essentially a landscape. Now, there are a few misconceptions here that people tend to have, which is that IoT is a dry field. There's not much of stuff happening there, which is far from the truth, as we'll see. And there's this big misconception that you need to be a system level programmer. You need to be very good with assembly, C, Arduino, and all of that, which is not true, because there's only one layer of IoT which requires you to be good at that, and that's the device layer and the device software layer. On top of that, whatever is built, that is all high level software. So it doesn't matter if you're a Java developer, if you're a Go developer, if you're good at Python, if you're good at C++ for that matter, you will find work at every level of IoT. And that's the best part about this. One of the things which I haven't mentioned here in these layers is security, which we're going to talk about in detail subsequently, but that is also a domain which is very, very important to IoT. Let's see. So coming to market share. Now, IoT device market share can be measured in two ways. The first is the number of devices, and the second is the revenue from it. So if you talk about number of devices, currently we are at around, I think, 50 billion. And the number of IoT devices is, so in 2015, you had 127 per second. And right now the number is much higher. And the prediction is that by 2025, you will have 75 billion IoT devices in the world. Now, why is this the case? Now, this is not the same for smartphones, because in smartphones, what happens is after a particular time, once everyone has a smartphone, that number declines. The number of people buying new smartphones is going to decrease. Whereas in IoT, you have got two very important things. The first is that the price point is much, much lower. So you can buy these smart IoT products from as low as 300 rupees on Amazon today. And you don't need just one, you need multiple. So for example, if I've got a smart bulb in this room, I want another in that room and the room after that. And you just keep buying these products. And because the price point is lower and the requirement is higher, you're going to see a huge number of IoT devices going out. The other important thing is that you get a lot of variety in them. So for example, today I just want to do lights. Maybe a few years down the line, I want to do my locks, then the thermostats, then my water heater. So on and so forth. As the needs keep on growing and as we keep getting lazier, the number of internet connected products that we want inside our homes is only going to keep going up. So the estimate for 75 billion is almost going to be true. And it's a huge number. 75 billion is a huge number of devices. So in talking about revenue, so it's around 96 billion by the year 2023 is the expectation. And that's a huge number of funds which are being pushed into this market. Now, they're typically going into three sections. There is device, there is connectivity, and there's software and services. So when I say device, it's the actual chip in that devices and the housing of it and the actual product which is built. Then there's connectivity, which means there is, so people buy routers due to IoT devices. Then there is connectivity chipsets which are being built specifically for IoT devices. There's a lot of stuff happening in the connectivity side just for IoT. So for smart cities, they're building cellular IoT devices, etc. And then there is software and services. So as we said, all of the IoT stuff needs an application layer on top of it. And that is what the service sector is about. So overall, the IoT market size is huge and it's only going to keep growing. And we talked about the reasons for that. But the question is, are they doing this right? I'll tell you a small story on that. So IoT has been a security and privacy nightmare in the early years. Now, why is that? So I'll give you an example of something that happened. So in October of 2016, almost the entire internet went down for some time. And when it was investigated further, the reason was found to be IoT devices. How? So there was a botnet which was designed. We'll talk about botnet shortly, named Mirai, which is Japanese for future. Now, this carried out a DDoS, which is a distributed denial of service attack, on DYN, which is a DNS provider, and it took down almost the entire internet. So how does this work? So what happened was, in the years leading up to this, companies were trying to come out with IoT products as fast as possible, because time to market is something that is very, very central to how IoT products are bought by consumers and how companies look at IoT products. So if you're late to the market, then there's absolutely no point, because if someone comes out with a smart XYZ device first, then people are likely to go and get that one rather than yours. But in that race to get first to the market, what these companies did is that they neglected one of the most important aspects of internet connected devices, which was security. And so these were running small Linux firmwares, which are very, very downsized, and they hardly had the entire network stack. But the main problem with them was that they could not be patched remotely. There was no OTA at that time, which is over there updates. And they were put in physically remote locations, or they were in inaccessible locations. So overall, what it meant was that once a device is bought and it is put up somewhere, that is the last of it. As in, the software running on it is never going to get updates, and it's going to keep remaining in that exact firmware for its life. But what Mirai was able to do was, it took advantage of these insecurely created products, which had default username and passwords, and they had just needed 61 username passwords, and they were able to scan for telnet ports. Now, telnet is an unsecure way of communicating with Linux-based machine, and using these default 61 username password combinations, they could get into most of them. Now, at that time, the market was already in billions. So there were billions of devices out there with default username passwords and open telnet ports. What that led to is that you could have a huge army of devices which could send requests to whichever target you wanted at whatever point in time. Now, let's talk about how it could bring down the internet entirely. So they targeted what is called DYN. Now, DYN or DIN is one of the largest DNS providers of the world. It is called the backbone of the internet. So let's quickly go over what DNS is and how it works. So DNS is a translation service, or you can call it a directory lookup. Now, when you want to access a website, you don't access it by IP address. You access it by the URL. So let's say I'm putting www.google.com. So my computer is not going to google.com. It's going to a server that has google.com hosted on it. And this server has got an IP address. And computers, the way internet works is that you always get an IP address, and you are always communicating with an IP address, not with a URL. So to map these URLs to IP addresses, we have got a DNS service. So DNS is also hierarchical in the sense that your request first goes to your internet service provider's DNS. If they don't have the IP for it, like for example, if I'm requesting a new type of site and they might not have the DNS entry for it, then it will go up higher up in the hierarchy and ask someone else for it. So you have got a TLD, you've got a root DNS, and you've got an authoritative DNS. So this is the typical DNS infrastructure, right? Now, what happens if I take down one of the bigger DNSs of this hierarchy? What happens is that, let's say Amazon.com, it's not down. So Amazon is not down. But if the DNS goes down, then I cannot resolve the address for Amazon.com. And when that happens, then I cannot access Amazon.com anymore. So this was something which they were not exactly planning to do. The hackers which created Mirai and they were using it, they were actually trying to hack the game Minecraft. But what ended up happening was that they ended up hitting servers of DYN. DYN went down, and with it went down a number of sites like Amazon, there was Airbnb, etc. Many of the big sites, Twitter, they all went down. The reason is that because the DNS was not functional, people could not resolve those URLs to IP addresses. And that's how you ended up with this problem. Previously, I had asked a question here, except one company, and if you have any guesses. Now, the company which did not participate in the sense that their devices were not a part of the Mirai botnet was Apple. So Apple from the very start had a very different approach to IoT devices. When everyone said that we would allow them to go out as quickly as possible, what Apple said is we want these IoT devices to have its own crypto chip and its own chip which we give you. In the sense that Apple has got something called the MFI chip, which is the made for iPhone, that's their branding. And that chip needs to be put in every HomeKit enabled product before it goes out. And because of that, the entire network operation of that particular IoT device is in an encrypted fashion. Now, later on, the industry caught up to this, and now we have got IoT devices which are able to do security really, really well. We have got on-device crypto chips which are able to do these computations for encryption very quickly. And Apple has moved on, and instead of a physical chip, you can now get a soft MFI also for your product. So it's not necessary to get that chip from Apple anymore. But the point is that the main emphasis on security was not there. And one of the worst parts about it till date is that the Mirai software is available open source on GitHub, and you can pretty much clone it and still use these, because as we talked about, that these devices are still out there. They still have those open ports. There have been no updates because there's no way to update them. And it has just remained in that state of limbo. So Apple did do really well with that particular product. But the problem which they ended up with was that there are not enough HomeKit enabled products out there today. So because of their additional requirement for security, they did not end up shipping way too many products. But I think they're okay with that because they're not playing that kind of a get to the market immediately kind of a game. Cool. So how do we solve this security nightmare? So security nightmare is now being solved by on-device crypto chips. There's the privacy nightmare. So how do we tackle that? Now, privacy nightmare is because, as you can imagine, IoT devices have sensors. They might include cameras. They might include microphones. They might include just data sending, whatever they are seeing or hearing. And there's no way of knowing internally what the IoT device is doing. And having such a device or more than one such device at home is a privacy nightmare in itself. So what can companies or we as developers do to solve this problem? So let's talk about that. So to enable privacy on IoT products, we're going to have to go slightly back in time and look at a history of how compute has been. And then we have got a new type of compute paradigm. So let's talk about that. So compute infrastructure over a period of years has been going through cyclic changes. So we went with centralized first, then we become distributed, we become centralized again, and then distributed again. So let's see how this has gone. So there was, in the beginning, there was one big computer, which we called mainframe devices. And then slowly we moved on to the client server era, where from central you went to slightly distributed, where you could have a particular server and a client connected to it. Then came what is called the cloud, which we see today. Now the cloud is again very, very centralized because everybody connects typically to one cloud. So you can have all of these multiple internet services running all of AWS. So if tomorrow something ever happens to AWS, which it happened recently, a lot of these services go down. So this is the centralized aspect that we have come back to. Now, what we are moving on to now is edge. Now, what is the edge? So edge is basically computing that is done at near the source of data. So instead of sending the data to a particular cloud service and having the data centers do all of the work, you keep the data very near to the source and process it there itself. So the processing is happening outside the data center and closer to the end user. Now, why is this important from a privacy standpoint? So the question to ask here is, do we need to rely on a cloud server to do a simple task of turning on a light bulb? Now, if you look at how this will work today, is that you have a light bulb, which is talking to the internet. You have got your phone, which is again talking to the internet. You send a request to turn on the light bulb from your phone. It goes over the internet and goes to the bulb. Now the bulb is right in front of you, but the request is going through the internet. There has to be a better way of doing this quickly because the device is right in front of you. So this can be done by local control, which is one of the other things. So you can have edge in two ways. So one way of doing edge is where you allow the user interface to become a part of the IoT device itself. For example, it can be a voice-enabled IoT product wherein you can talk directly to the IoT device rather than having to rely on a particular server. Or what you can do is you can have local control, wherein your mobile app can communicate with your device over Wi-Fi or Bluetooth rather than having to rely on going through the internet. Now, this is essentially useful for many tasks like, for example, a burglary system. So there is a webcam which is put up, connected to some kind of a Raspberry Pi or any other embedded system. And what is happening is that every time there is a frame change, that is 2 frames which the CCTV is looking at, if there's a lot of difference between them, you want to raise an alarm. Now, if you are processing this video elsewhere, then the video is going to take time to get uploaded first, then processed there, and then it's going to be sent out. Now, this chain can be made much smaller if you just take the computation and bring it on the device itself. So you need not have to go through this entire chain, but rather the device itself can compute it and quickly give you the result. For example, if you need to activate an alarm system based on a burglary detection system, then that can be done very, very quickly with edge computing. So why why is everyone interested in this edge thing? So there are 3 main aspects to it. One is reliability. Now, reliability means that if the internet goes down, the device does not stop working. Now, why is this so relevant? Now, this might not be very relevant for consumers. For example, if my light bulb stops working because the internet goes down, it would hardly be a life-threatening situation for me. But imagine industrial IoT, imagine medical IoT devices. You do not want them to have the internet dependency. What if the cloud goes down? What if the internet goes down? You cannot allow these things in case of mission-critical devices. Some applications just cannot rely on the internet being the main connectivity medium. Offline reliability makes all the difference. But then there is privacy. So privacy is very, very central to people today, where we don't buy products which don't have a proper privacy policy. We don't want to put microphones in our house. We don't want to put cameras which are internet connected because security might not be that great. We don't know what they're doing with the images, etc. Edge computing helps alleviate most of these issues by doing the processing on the device itself. And lastly, there is latency. So we talked about how for a smart bulb which is right in front of you, your phone needs to go through the internet to communicate with it. This adds a lot of latency. It's almost in the seconds. So for example, 10 seconds sometimes to change a particular configuration on your light bulb. With edge computing or local control, you can have this happen very, very quickly. Wherein in almost milliseconds, you can directly turn the light bulb on or off, or do multiple things with it. Now, this is not just important from a UX standpoint, where the user experience is much better because it's faster. It's also important for mission-critical applications. Another important thing here is cost. Now, this is a less talked about problem of IoT. Now, when the companies are manufacturing IoT devices, they are not taking the cost of the cloud in mind. For example, I might buy a ₹200 bulb from a particular company. Now, for them, they have made the bulb, they have sold it to me, I purchased it, they made their profit on it. But they're going to need to keep the cloud servers running for life. And that cost is not necessarily being imposed upon the consumer, it is being borne by these companies themselves. And if you're a smaller company, if you're a startup, then the cloud costs are going to add up much faster than all of your other costs combined. And this problem is something that can be solved with edge. But I think there's a problem in this, because we talked about how the IoT devices are sending data to the cloud, and then the data can be analyzed, and there is data analytics happening, so on and so forth. But the question is, with edge, if there's no data being sent over to the cloud, what happens? So if edge implies less data, how do we do machine learning on it? So the answer to this is interesting, and it's called federated learning. So I'll explain what federated learning means. In federated learning, you have got one centralized model. So let's say it's this blue one here. Now this model is downloaded by every device which is out there. Now I'll give you an example of mobile phones first, and then we'll talk about how this can be used for IoT. So now this is being used by the Google Gboard keyboard. So if you have been using that on your Android phone or iOS device, then you are using federated learning. So how it works is there is one global model for typing prediction. So it gives you these predictive texts which are happening. So there's one centralized model for that. When you download Gboard on your phones, this model is downloaded onto every phone. Then this adapts to the user's own typing experience. So it kind of overfits on how that particular user types, and it is giving him very specific tailored predictions based on how he or she types. Now this model is then used to retrain, this data is used to retrain the model on the device itself. Now this delta, that is, so the original model versus the new model which the device has created, the delta of this is taken and the delta is sent back to the central model. So what is happening here is that there is no data which is ever sent. What is sent is the learning from this data. So if you look at the ABC here, so there is a model which adapts to the particular user. Then there are many such adapted models because everybody is using it differently. And the change, that is the delta, is sent back. And only the delta is used for making the centralized model better. So essentially, there is no data being sent. It is just the learnings from the data which are going and improving the central model. So we can still get the machine learning benefit without ever having to get the data off of the device. So this is one of the great things about federated learning. Now, this is possible very simply in case of smartphones because they are powerful enough to do the compute on their own, as in on the device, the models can be retrained. Whereas in case of IoT, this is not very commonly seen. However, we do have more and more powerful IoT chips coming out, and they can allow these kind of things to happen. For example, if you have an Alexa device at home, this Alexa device can theoretically learn from the way you speak to it, improve its own model, and then send back this delta to the Amazon systems, and that's how they can learn. Because currently what happens is every voice recording that you create, that is whenever you talk to your smart home at your smart home voice assistant, all of these recordings are sent back, and those are used to retrain the models. Now, this can be changed with the federated learning model. So this is one of the ways which we can use edge computing. Now, then there is another interesting paradigm, which is moving your model to the data rather than the data to the model. So this is what we talked about before, but what is happening here is that you have got on-device accelerators which can carry out AI operations. So now this is very commonly seen in phones where you've got neural engines and neural processing units, NPUs, which are being put, and of the device itself. Now, what you can see, this GIF here is there is face detection which is happening of a microcontroller, and that when the face is detected, it is sending an email over using an SMTP server, and the image is seen on a mobile phone. Now, this is possible only with something called TensorFlow Lite for microcontrollers. So a lot of the IoT devices which are available today, they're using microcontrollers and not microprocessors because they're much, much cheaper and much more fine-tuned to that particular use case rather than microprocessors, which are general purpose and essentially heavy compute devices. So with TensorFlow Lite, what you can do is only within a few kilobytes, you can have an entire model. Now imagine an entire machine learning model running on a microcontroller. And this is happening today. In around 16 KB, you have got an entire face detection model which is happening. And because microcontrollers are so common, and they are already in billions of devices, IoT devices around the world, with this one TensorFlow Lite, you can make all of these microcontrollers much, much smarter, and they can take decisions on their own without having to rely on the cloud. So cutting down cloud costs, as I said, is very, very important to companies, because imagine that you have got a microcontroller, a camera, on the microcontroller, and now you are trying to do this image processing on your end. Imagine a billion devices out there today which are not able to compute themselves. You're getting all of these images, even if they take one image each, which is obviously a very conservative number. If you have to process those many images, how much of cloud costs are you going to bear? So edge computing and moving the model to where the data is very, very important to IoT. Up next generation interfaces. So we talked about this before, and what we are trying to have is a voice user interface which does not rely on the cloud at all. So currently what is available is that the hot words and the wake words, for example, Alexa or OK Google, these hot words are detected offline by these devices. But anything after that is being sent over to the cloud for computation. However, this is now slowly changing. So if you have the Gboard keyboard installed on your devices, you can already take advantage of on-device voice models. So Google has been able to compress the entire offline, so the entire voice recognition to an offline model, which fits in, I think, around a gigabyte or something. And they're able to do completely on-device voice recognition. So this is very, very important because currently you have smart speaker adoption, which is going really, really high. So almost 53 million people in the US today have got at least one voice-enabled product in their house. And this number is set to increase to around 275 million by the year 2023. So you can see that the growth has been around 1,000%. But the rest of the market, the reason why it's not popular everywhere else is because of privacy concerns. And if you can manufacture or create devices which can do complete voice-based input on the device itself without having to talk to the cloud at all, then you can get a much better product. For example, a washing machine, I go in front of it and I say, rinse cycle 30 minutes. And that's it. And I don't need to talk to the internet. I don't need to talk to Alexa at home, etc. So this is a next generation interface which solves the privacy problem. Then there's been a big issue with IoT, and that has been standardization. So standardization is a problem with IoT because we talked about how there are very, very different devices. And what the consumer expects is that you bring these IoT devices home, you plug it in, and they start working. But that is very, very far from what we are doing today. So today what happens is, now imagine you have to buy an IoT product. So it can be a door lock, it can be light bulb, switch, sensor, anything. You have to first consider what network you have at home. So whether you've got a Wi-Fi only network, whether you have got a Z-Wave router, a Zigbee router, what your other existing devices already have, which assistant do you have at home? Do you have Siri? Do you have Alexa? Do you have Google Assistant? Does this work with this assistant? Does it not? And other devices which are already in your house. So only after you consider all of these things can you go ahead and buy a product. Now, this is what we call defragmentation, wherein devices don't play well with each other. For example, if I purchase a product which does not have an Alexa skill today, then I will be forced to use Google to control that device over a voice assistant. But if I already have Alexa at home, then it is useless because I can't control that device. And I need to check this before I purchase the product. This is overall a very bad experience. The bigger problem is that you need to install an app for every particular manufacturer. For example, if I purchase a Samsung air conditioner, then I've got a Samsung app to set it up. If I buy, for example, a Wipro smart bulb, then I'm going to need a Wipro app to set it up. So there is a lot of contention amongst these devices, the protocols that they use, the companies which make them, and this is a defragmented field currently. So what we are trying to do today is solve this problem by using something called CHIP, which is Connected Home over IP. So this is a new project which is under the Zigbee Alliance. And what it is doing is that it's bringing all of these things under a standard open source model. Now, for something like this to succeed, what is important is that there are the main partners which are on board. So partners include chip manufacturers, they include voice assistant manufacturers, and they include cloud providers. And luckily, for now, at least, all of the people which are relevant in this market today are already a part of or are slowly coming into the CHIP Alliance. which already includes big names like Amazon, Google, Facebook, etc. Now, once this protocol is finalized and once all of the companies which are relevant are on board, what is going to happen is you're going to have a layered stack like this. Now, if you see, this is operating over IP. Now, IP is the most standard protocol for the internet. Almost every device uses it. However, there has been no standardization for it in the IoT market, which is unlikely, but it's the case right now. So what chip does is it creates a layer on top of all of this, which allows you to use only the chip layer, and internally it figures out the networking part. So what you get overall is that if your device is chip compliant, and if the manufacturer for your phone is already on board with the chip alliance, then what you get is you can directly bring in the device at home, connect it to a power supply, and directly configure it without using any apps from the operating system itself. And this is sure to work with your existing voice assistant and all of that. Now, I just want to see if there are any questions right now from the IoT side of things. So, yeah, let me just take a few questions right now. So, can we learn Node instead of C++ for IoT? Is it recommended? Okay, that's a great question. Now, there was a project named Node MCU, which was very, very popular, running on the ESP8266 chip. And yes, Node is a great thing, and it's much simpler for a lot of newcomers than something like C++, which tends to get heavy. So instead of using the word instead for Node, I will recommend that you brush up on your C++ skills and then you jump onto something like Node. The reason for that is a lot of the production-ready devices today are still being written using slightly lower level languages like C and C++. Of course, you have projects which happen over Node, but if you look at the industry standard, then it is generally happening over something like C or C++. Yes, Node is there and it's simpler, but I will not recommend doing it instead of C++. I would want you to have a background in C++ and then move on to something like Node. Time series as in discrete or continuous, like we generally see discrete values from sensors. Yes. So time series database will have discrete data points, but when you put them in some kind of a graphical format, you want to be able to see them as a graph, as in how has the value increased over time, decreased over time, so on and so forth. So even if the values are discrete, we are doing visualization with these things. Which job roles are generated in future because of increase in IoT field? So let me go back to that slide and give you an idea of the job market here. So this we discussed already, but to give you specific jobs, if you look at the device side, let's start with the device first. So in device side, you have got the device hardware itself, which is the chips. So for example, I currently work with Espressif, which is manufacturing chips for IoT devices and connected software. Have a chip coming out, then you have to provide the software and the SDK which goes along with it. SDK is another important aspect to the IoT platform, because whenever you create IoT products, as in if you are making a new chip for IoT, then these hardware which you have come out with, like the chips, they need to have an SDK. So only then will a manufacturer will be able to take your chip and combine it with his application logic. So you need to write the SDK for it as well. This is where embedded engineers or embedded software engineers, system programmers are commonly seen. Then there's the sensors. So when it comes to sensors, a lot of people from the instrumentation background, etc., are required to create newer kind of sensors to be able to sense various things in the real world. And then there is design. So design here is product design and also chip design to some extent. So chip design is also a very interesting field. So if you're from an ENTC background, then chip design is something that is now much more in demand because of things like RISC-V, which have come out, which is an open source instruction set architecture for making chips, where you don't have to pay royalty to some company like ARM for the instruction set. And the other aspect is product design, wherein the IoT device, so someone looks at the internals of it, but someone has to see about how it is going to look on the outside. As in, if you buy a Roomba vacuum cleaner, you want it to look really good. If you buy a smart home speaker, then you want it to look presentable and something which you can keep someplace in your house. Then coming to the network side. So network hardware. Now this is where you get into antenna design. So this is an actual topic for a lot of people pursue it as their masters. And also you are taught it in the ENTC engineering departments, wherein there are many ways of making antennae and making them smaller, more robust, more reliable. It's an entire field. So that's a job role. Then there's network software. So this is network engineers are what they are typically called, and they are either writing drivers for it, or they are doing the testing for these aspects. They are either writing the abstraction layer, which we talked about earlier for the network devices. Then there is algorithms. So this is a purely algorithmic field wherein for solving problems like congestion or latency, you have to come up with algorithms, because these things, they are not completely hardware solvable. You cannot keep making better hardware and make your networking better. At some point, you have to make your algorithms more optimized. So this is even more relevant for the IoT field, because we have got memory constrained devices which are out there, and they need much better algorithms to be designed. And algorithm design is itself a big field and a job description. Wi-Fi and Bluetooth. So yes, this also means chips and it means drivers. So someone needs to understand the Wi-Fi spec and implement it on a particular chip. And this is not as simple as it looks or sounds, because we are generally used to buying off-the-shelf devices which come with the Wi-Fi or the Bluetooth built in, or we already have drivers for it which we can just install and it works. That is not the case for companies, because they have to actually write those drivers, they have to make that hardware, they have to comply with the standard. So there is a Wi-Fi alliance group which they sit together with these companies and they ensure that there is interoperability. For example, if your device wants to communicate with a router, then both of them have to agree upon a certain set of things. And this is a regulated field. There is the FCC, there is IEEE, which does the standardization. There is the Wi-Fi Alliance group. So all of these things happen, and this is a proper job description. People in companies are assigned this task of getting that done, getting that particular Wi-Fi module certified for use. There's also different things, like in countries, you've got specific channels for the Wi-Fi. So in Japan, there's one channel which you can't have. Then there is interop which has to be figured out. Many things happen. There's also mesh networking, which is coming up, wherein you create Wi-Fi routers which are able to create one network rather than a series of multiple networks to solve problems like roaming and the sticky situation where your device is always connected to a particular device, a particular router, rather than switching between them. So there's a lot of interesting stuff happening in the networking field. Coming to application, web backend, as we talked about, is a field in itself. And you can be a programmer in anything. So now a good thing about web backend is that you can be a web backend engineer in any language, and the companies will not care much about what language you're making the backend in, as long as you are writing the proper API for it. So this is one of the best things about the web, wherein everything, as long as it is RESTful or complies with some predefined format, you can use it. So it can be RPC, it can be REST, it can be SOAP for all intents and purposes, and you will get that web backend stuff. Web frontend is a very fast-changing field. There are JavaScript frameworks which are coming out very often. The field tends to change very rapidly, so you have to keep moving up. Earlier, we had was Bootstrap, then we got these Angular 1, 2, 3, so on and so forth. Then we now have React, there's Vue. There are so many JavaScript frameworks, and typically what we suggest is that you stick to one, and once you understand the way one works, then you can use that knowledge for all of the other front-end frameworks. but front end today requires very heavy JavaScript usage. So if you're thinking of getting into front end, HTML, CSS, JavaScript is your thing, and you need to be very good with that. So, but it's a great job description and it's a proper job. Then there's cloud engineer. So the cloud problem in IoT is manifold. So the first aspect of it is the device connecting to the cloud. So this happens over things like MQTT or other services, or it is only in REST. So you have to figure that part out also. And as we talked about before, AWS and companies like Google Cloud Platform or Azure IoT, they have their own IoT products which are built. So how do we create a product which is not cloud specific, but it is cloud agnostic? How do we have cloud infrastructure that can scale up with number of devices? Because we talked about how IoT devices can run into the billions. This is never the case for a normal web server, when it is only replying to a typical number of requests every time, because you only have those many devices. But when it comes to IoT, the number of devices are so huge that you need to have very robust and scalable cloud infrastructures that can allow for these many connections to take place simultaneously. So there's the device to the cloud part, then there is the cloud scaling itself, then there is the deployment of your backend on the cloud, which is another thing which needs to be done. And that is more of a typical DevOps pipeline, but it also requires a cloud engineer. And so there is also cloud engineering, as in from an architecture point of view, you have to understand how these systems will interact, whether you should go with serverless, which is a new upcoming thing to cut down costs, whether you should go with a typical backend model, which model to choose, how to scale, whether this should be containerized or not. There are many questions which cloud engineers have to answer. And you can either specialize in a particular thing. So there are many certification courses. There's AWS certified. There are hundreds of courses on that. You can specify AWS cloud, IoT specific courses are there. Many courses are there. So cloud is a big thing. Then there is databases, which either the backend engineer or the cloud engineer handles, but you need someone to design the database itself. API design, again, taken up by either the backend guys or the database folks, but this is again an important part and will be a part of your job. Mobile app development is one of the big things that you can do right now, because there is so many ways to make apps today. You can have native Java or Kotlin based Android apps. You can have native iOS apps. You can make them using something like Xamarin. You can make them something like React Native. There are many options which exist. And companies are going to keep needing mobile apps, at least till something like chip is finalized. And even after chip exists, there will continue to be applications to allow for a greater level of control. And mobile apps are going to continue existing. And mobile apps is a job description which can help you work in almost any company today, because most of the companies have to come out with a mobile app at some point or of time in their lifetime. So that's a good job. And UI and UX. So we talked about this before. Apps and the web front end are both going to have a UI UX component. And really good companies invest a lot in UI UX developers. They just have to design it and send it forth. They don't have to write any code. So if you like to design things and you're not very good or very interested in coding, which is completely fine, you can look into UI UX courses, and there are softwares like Sketch, Figma, etc., in which you can mock up these designs and you can send it ahead. And then the coders or the developers of the team, they are assigned with the task of creating that actual interface in code. Testing and DevOps. So testing, so there are test engineers which are required. You have to write test cases for your IoT SDK. You have to write test cases for your backend. You have to write test cases for your apps, for your algorithms. For almost everything that we talked about before, there has to be testing which is done. So there is physical hardware testing which happens in case of chips and sensors. There is software testing which happens for everything else. And then there is DevOps, which how we talked about deployment of various things. How do we deploy them to the cloud? How do we allow integration to happen when the code changes? How do we change the deployed code? Things like that. So DevOps roles are available. Analytics, yes, data analytics is a proper job description. data science folks, people who have done courses in data science, machine learning courses, they're all being hired by IoT specific companies because they've got huge amounts of data, more than you can imagine. So when we talk about deployments in the range of billions, we already know that there are going to be a huge chunk of devices out there generating data all the time. So the amount of data is huge, and you need someone dedicated to look at the data and give you analytics on that. And we talked about predictive maintenance and other things. So machine learning engineers are employed for this particular purpose. Yes. So next question is basically FL, which is federated learning, has got a local model training and a single global model on cloud, which ensures security. Yes, that is correct. So let me jump to that slide. Yeah. So just to recap what we talked about in federated learning, we do have local model training, which happens on the smartphone or on the IoT device. So yes, there is local training which is happening. And there is a single global model, yes, which is being trained based on the deltas which we send. So a delta is basically only the difference between the two models. So there was a global model, it was downloaded, it was retrained on the custom data of the consumer. And now you have got a difference between these two models. And only that difference is sent back to the main central model. And that's how the central model improves. So once the central model improves, you can get that central model back into the devices again, and that's how the whole chain works. Does it ensure security? Yes. So the correct word to use here is privacy and not security, because data can be sent securely anyway. The problem is not that someone else might steal the data. The problem here is that the data is private, and I don't want that data to be sent across over the internet. So what we are looking for here is privacy to be ensured, and this model does not permit any data to get sent, and that's how we get a much better product which does not send your data over the internet. What is the roadmap to be followed for IoT security? Okay, so yeah. Now, the security aspect in case of IoT has been solved for the most part, because any mature IoT product that you buy right now will come either with some kind of encryption algorithm like TLS, like in the sense embed TLS, or there is Wolf SSL. So such things are generally available on your device when you purchase it. So all of your communications are going to be encrypted. Secondly, we now have devices which are coming with on-device chips, like what Apple did in case of MFI, wherein you can have these cryptographic computations. Now, what happens in the case of security is that you need to do a lot of data encryption before you can send it ahead. And this encryption is a costly operation in the sense that you need time and compute capability on the device itself before the data is sent. And there are lightweight TLS utilities like Embed TLS and Wolf SSL, which allow the data to be encrypted before they're sent across. But now, because you have these on-device crypto chips, you can do this in a much faster manner, and you can encrypt almost everything. Another interesting thing which happened was that there was a manufacturer for light bulbs, and they made these light bulbs and they did not invest a lot. So they did all of the TLS part and the communication was secure. The problem was that the firmware itself of the bulb was not secure. So a lot of people, these consumers, they bought these bulbs, they connected them to the Wi-Fi networks, and then they threw away these bulbs. So someone got a hold of this bulb from the garbage can, opened it up, connected it to the computer, found that the firmware was not encrypted, and he was able to get the Wi-Fi passwords out of the device, and then he could connect to that person's Wi-Fi network. The point is that when we talk about IoT security, it's not just about the communication that needs to be secure. It's the device itself that needs to have flash security, in the sense that if someone connects this device after it is burnt, as in once the firmware is burnt onto the chip, if someone connects it to a computer, they should not be able to get data from the IoT device. And this has also been neglected because nobody really expected people to go around plugging in these devices directly to computers, but that happened. And so lesson learned. And now we have got something called secure boot, secure flash. There are many things which are happening for on-chip security. So yes. So in terms of giving you what you ask for a roadmap, the idea is that choose a mature platform, ensure that it has chip level security from point of view of communication, as well as flash based security, which is for the chip itself to have to store data securely. So I think that should be it for security. I might be missing something here, but if you ensure that these two things are in place, then you can expect for the most part, you can get a good and secure IoT product. What skills are needed for IoT pen testing? Oh, that's a very interesting question. So pen testing or penetration testing, for those who do not know, is a field wherein you have devices or networks which you try to break into and check whether they can be broken into, whether you can attack these devices in some way and get information from them. Now, when it comes to IoT, again, so this is going to work in tandem with the security model. So in the security model, there's chip level security and there is communication security. So similarly, in the pen testing, you will have chip level pen testing, which happens, and then there's going to be a communication level pen testing, which happens. So let's talk about both of these. Now, in chip level pen testing, you generally have to be very good with hardware. In the sense, you need to be able to debug over JTAG. You need to be able to figure out how you can talk to this device once you connect it to the computer. You need to be able to decode the raw bytes which you get, figure out how it is encoded in the first place. So it's almost an embedded reverse engineering job profile, wherein you understand the connections, the chip, and how it works. So that will then give you insight into what is actually going on inside the chip. So this is so if you look up reverse engineering, so there are tools which are based on this, and there are people who analyze instructions. So there's this thing called a timing attack, wherein you see the time it takes for a particular computation to happen, and based on that you can predict what the computation was or what was happening in the background. So such attacks, they require precise electronics knowledge, and there are tools which are based around this, where you can take the assembly code and you can reverse engineer it, see what it is originally doing, get strings from the device. So that's the hardware aspect of it. From a soft aspect or from a communications aspect, you can do pen testing based on what we call communication testing. So there is Wireshark, which is a very popular tool for network analysis, wherein you analyze the packets which your IoT device is exchanging with the internet, as in your particular router at home, and then you check with the data which this packet contains. Now, previously, when IoT devices first came out, they did not have a very good TLS or secure HTTP infrastructure or code on top of it, because there were no libraries at that point which were working for embedded devices. And because of that, the data was being sent over HTTP. So anyone with Wireshark and a packet capturing device, like even your laptop Wi-Fi chips, they can capture it in monitor mode. So even with that, you could figure out what data is being sent, and you could capture this data. Now we have got Embed TLS, Wolf SSL, and other platforms which are ensuring that there is packet level security which is being there. As the transport layer is secure for IoT devices. Yet there are possibilities that do exist where some data is being sent over an unencrypted medium. DNS requests, for example, they're happening over UDP. They're not typically encrypted, and you can figure out a few things from that. So to answer your question regarding pen testing, there's going to be two aspects to it: the chip level, as you talked about, and then there's going to be the communications aspect of it. So let me see if I got through all of that. Node is done, time series is done, job roles, federated learning, roadmap, and skills for IoT pen testing. Is there anything else, guys? Mhm. So if there's nothing else, then we can go on to the robotics aspect of it. If you have any IoT questions, you can feel free to send them in right now. I'll wait for a minute or two. Just to extend on the first question, can we learn Node instead of C++? Um, so the barrier, as in the entry point for IoT, has become much, much simpler. So there's something called MicroPython, which is come out recently. And what it essentially is an entire Python interpreter which runs on microcontrollers. So obviously it's not the entire Python with the standard library. It's a small subset of it. But what it allows you to do is write programs in Python for your microcontroller. I think just a second. Okay, so if there are no more questions, guys, no more questions, right?
Yes, sir, you can continue.
Okay, cool. So moving on. We talked about chip. Now let's talk about robotics. So as it was earlier introduced, robotics is intersection of science, engineering, and technology to produce machines, which we call robos or robots, that substitute or replicate human activity. Now, robotics is one of the most interdisciplinary fields in the world today because it encompasses almost every possible thing that you think of. You think of electronics, it's there. You think of mechanical, it's there. You think of computer science, it's there. Purely algorithms, it's there. Software, it's there. Hardware, it's there. No matter what you think of, it's going to have some role to play in case of robotics. And it has also given rise to a completely new field called mechatronics. Now, what I feel generally in case of robotics is that you have to be passionate about at least two fields of engineering in order to make an impact in robotics. What I mean by that is if I am purely interested in software, for example, then I might be able to make algorithms for robos. I might be able to write the software stack for robos. But the thing is that my ability as an engineer for a job profile in a robotics based company or environment is going to be limited because I only have knowledge of that particular aspect. Now, if I combine that with, let's say, mechanical knowledge, then what I have is I am able to write software and I understand the mechanical aspects of it. And only then is my value proposition as an employee going to have some value in case of a robotics thing. Or you can have something like software and design, wherein you can design a robo and you can write the software for it, in the sense that you design a servo or the arm for the robo, and you're able to write the code for it. Or you can have other combinations which are happening. But the idea is that you must have knowledge or passion about at least two fields within engineering in order to make an impact in robotics. So this is not a hard and fast thing. It's just whatever I have observed that people are doing today, and what I see companies in their hiring. This is what is seen. Okay. Now, I'm not going to introduce robotics because it's firstly it's very, very huge and it goes into many different fields. You've got medical robotics, you've got consumer robotics, you've got industrial robots. It has got many fields. And it's also not as new as IoT for most people because almost everyone has watched at least one movie which introduces the concept of robots to them. So they're familiar with the idea. With IoT, it's a much newer atmosphere and things are different. But when it comes to robotics, we are all pretty familiar with it. What we are not familiar with is the new things that are happening in the robotics field. I want to talk about one of them. So the latest in robotics is not building a robo. So as odd as this sounds, I want to explain this further. So the robotics field is a costly field because so the only people who are working heavily in robotics are companies, not companies. So there's companies and there is research institutes which are heavily funded. So there is either going to be a company which is huge and they're doing a lot of other things and robotics, or there are going to be institutes which are heavily funded and they're able to do robotics. The reason for this is that the cost is much high, because much higher than now if you are making a software product, you don't have to pay much. You get a computer, you get an IDE or a text editor, and you can just start writing your software. When it comes to robotics, you need the hardware, you need to write the programs for it, you need to add aspects which are able to give it the thinking ability, you need processors on the robo itself. Each individual component in a robo has to be programmed separately. So, and then it's all connected to a centralized brain. So it's a very, very complex process which requires a lot of manpower, it requires a lot of time, it requires a lot of money and expertise, of course. So the field of robotics has been very, very difficult to progress in, to prototype, to move ahead quickly. So that's why we don't see as many advances happening in it as often, because not enough people can work on it. For example, in IoT products, you will find a new product coming out very, very quickly, because we talked about this earlier, the price point is much lower and the variety is very, very high. Whereas in case of robos, they're hard to build, prototype, test, and they're also hard to make. So it makes the whole idea much less appealing to developers like you and me. But this is now starting to change. We have very powerful softwares called simulators. Now, simulators have been around for a long time. We have had flight simulators. We've had we've had games which simulate the real world. Now, this is a screenshot, not from GTA, it's from software called Carla, which I'll talk about. But simulators have been around for a while. The thing is that simulators have become extremely good in very recent times. So what simulators allow you to do is you describe your robo in the format of a file. Now, this includes very minute descriptions, as in what is the inertia of that particular robo, which movements can the robo do, what is the exact, what are the exact dimensions of that particular robo, if there is a motor, how many degrees can it move, what speed can it move at. You give very minute details of the robo itself and the environment. The simulator then takes this description of your robo, puts it in the environment that you have specified, or simulators come with their own environments, and then you give it your algorithms. Now, robotics algorithms are, you will find this hard to believe, they're for very, very simple things. For example, there is an algorithm for picking things up. There's an algorithm for walking on a line. There's an example for following a path, for picking up objects, for every possible small action which we take for granted as humans. We can just pick objects up very simply. For robots, you need to program all of this. And one of the other problems that we'll talk about later is generalizing these things. But the main idea is that everything needs to have its own algorithm for carrying it out. Now, what this means is that for a simulator software, you need to give it a few inputs. So first, as we talked about, is the robo file, which describes your robo and its capabilities. The second is your algorithm, as in the code which is going to run the robo. And the third is the environment itself. So the environment can be whatever your test environment is, whatever your to-be deployed environment is, etc. Now, once the simulator has all these inputs, you can allow it to run these algorithms in the environment. So what that means is that you can see your robo in the environment. You can see it applying your algorithm and moving around and doing things. And the cost for all of this is nothing. You are not having to invest anything. You can directly design your robo in a CAD software. You can export it to a format which the simulator understands. You can import it into the simulator. You can write the code, import it again into the simulator and start running it. So basically the cost of robotics has come down to nothing. And that means from now onwards, the entry barrier is so low for robotics that almost anyone who has a computer, you need a fairly good computer for this, because simulation softwares, they're doing real-time computation. It is not a memory intensive process. It's more of a CPU bound process. So you're going to need a beefier CPU, probably a GPU. But if you have a fair enough laptop, then you can start off with robotics without having to buy any hardware at all. Now, of course, this is more of real life robotics. You can make slightly smaller, small scale robotics on your own. You can buy the hardware kits and do all of that. But those robots are not going to solve bigger problems. Like you can probably make like a remote controlled robo. But the whole idea of robotics field is to have autonomy in it. And for that, you need something like a physical robo that is made till now. With simulators, you can change this entire landscape and you can start off. Now, here what you see is Carla, which is it's a simulated driving experience for self-driving cars. Now, this is a big problem because self-driving cars, so one thing is field testing them, which is very costly because you have to have an actual car and you have to convert the mechanics of it such that you can control them via software. Then you have to write the additional software for it, connect all those sensors. It's a very costly effort. And that's why very few companies and none in India are able to do it. But with Carla, you can start simulating the environment and create your own self-driving algorithms and test them. The bigger concern when it comes to self-driving cars and that whole domain is safety. Now, you might have read about the Tesla car crash. You might have read about Google's Waymo car crash. So Uber also had a car crash recently. And whenever such a thing happens, you always have the question of AI ethics and what is right, what is not right, which is again a debated topic today. But the thing is, with simulators, you can have a much lower tendency of such effects happening, because before you field test, you can run these simulations in a lab in a safe environment, and only then you can go ahead with the actual self-driving car, which makes things much easier. Now, most of you are thinking that this is very much like GTA, which is true, because if you zoom in on the screenshot, what you will see is that it says PY game in the top. Now, PY game is a game engine which Carla is internally using. And so games have been very good at simulating things. If any of you have ever played GTA, then you already know that how realistic the games are today. So games and game engines have already been very good at emulating reality, and simulators are just able to use that game engine or the game-like software and build on top of it. So we already had these things. It's just that now, because the technology is more advanced, we can have very realistic simulators, and they can allow us to test robotics in a very safe environment at a very low cost. So if you're interested in building robotics today, you don't have to go out and buy anything. You don't even need to know how about physically building a robo. You can just download simulation software and you can go ahead and use it. Next, I want to talk about ROS. Now, ROS is the robo operating system. However, it is not an operating system. Let me explain what it does and why it is relevant. So let's imagine a robo. So it's going to have many hardware components. Each of these is going to require its own software. So even something as simple as an arm will have its own servo motors, and there will be a library that is used to run those servo motors. Now, put this arm on a wheelbase, as in you have got a wheeled vehicle, and you have got more motors and more software libraries to use those motors now. You add a particular sensor, then there is the sensor data which is coming in. And there is a library which interacts with that particular sensor. Then you have got a camera for vision, for example. Now, this camera is generating, again, a different kind of data. This is image data, which is heavier to process as compared to sensor data, like pure sensor data. So now you have got a completely different compute aspect to your robo. So right now, we have split the software into multiple processors or processes, one for the arm, one for the mobility aspect, as in the wheels, and there's one for the vision, and there's going to be one main process which is going to interface with all of this somehow. So a very simple robo can become very, very complicated very quickly. So the thing is that to make such a robo, you are going to need to do all of these things, get the libraries, get the software which talks to all these libraries. So the communication part is very difficult, and so ROS actually solves that. And you're going to need a brain to communicate with all of these components and tell them what they're supposed to do. So this is much harder than it looks. Robots that you see today are an effort of over 2 decades or more of next generation work that has happened in this field only, which has allowed them to come to that level. As I talk about, so vision will be either on a separate component altogether, because when you see these servo motors or arms, etc., they're typically embedded microcontrollers, which are not designed for high-level computations like image processing. So you will most probably end up in a situation where you've got 2 or more chips which are controlling each of these aspects, whereas so the image part is being handled only by one particular processor. The microcontrollers are handling the servo motors or the ARM, etc. So you're going to have many, many components here. So what ROS does is that it gives you a middleware, it gives you a set of libraries. It's not an operating system, it needs to run on top of an operating system. So it runs very well on Linux. Of course, there are ports for macOS and Windows which are in the work. But what it gives you is that it gives you that layer with pre-built libraries for interfacing, for image processing, and it gives you, most importantly, algorithms. As you talked about before, in robotics, everything needs an algorithm. You want to pick something up, it needs an algo. You want to do move around, you need an algo. You want to follow a path, you need an algorithm. You need to go somewhere, pick an object up, bring it to you. Again, it's a combination of these algorithms. So ROS gives you all of these components as pick up and drop modules. And one of the great things about that is you don't have to reinvent the wheel every time. So every time you will not have to create your own library for doing all these things, or write your own algorithm for doing all these things, because these algorithms are fairly complex and you and I might not be able to do all of it at once. So ROS gives you that test bed, it gives you the middleware on top of which you can start building your robo. And ROS is very, very popular. It has been, I think, in development since around 14 years. And it's very, very mature operating system in the sense middleware. It's not a complete OS, but it's a very mature platform. And it's being used in the Mars rover, the Curiosity rover used ROS. And it has got very, very good community support. So you can go to ros.org or github.com/ROS and you can check that out. It's a very good way to start building robos today. And this is something that almost every beginner needs to look into, because no matter what robotics company you get into, it's certain that they will have someone working on ROS for their particular robots. Now, what happens in industrial robots is slightly different. So in industrial robotics, every company has their own language and their own way of communicating with that particular robo. So when I say industrial robot, there are all these, you must have seen those car manufacturing videos where the robo comes in and spray paints the part, or it picks up a part and rotates it, all of that. So these are made by companies which are giving you the SDK to write it. So they're in their own languages, they're in their own frameworks, etc. But ROS is like an all-encompassing thing. So if you're making your own, then you can use ROS for it. It's got a huge number of libraries and tools, and it interfaces really well with simulators. So what you can do is you can create the virtual aspect of the robo, as in the software for the robo, and you can give it to a simulator like Gazebo or others. Now, recently, ROS has been working on ROS 2, which is the sequel to ROS. One of the big problems with ROS was that it required a host operating system to run, and it was a powerful computer. Like, the requirement is a high-end computer. However, it did not interface really well with embedded devices. So we talked about how servo motors or motors or these ultrasonic sensors, they will all have embedded RTOS MCUs. And ROS was not very well tuned to communicate with each of these. But with ROS2, they are trying to solve that problem where you have first-class support for embedded systems, RTOS like environments, these servo motors, etc. And now you can also run ROS on microcontrollers. So there is a port for ROS which is happening. It's called ROS Micro, and it's happening for the microcontrollers department. So once that happens, then you can have really cheap robos as well, which you can put. And ROS2 spec is, I think, final, and the API is much better. So one of the things which we said is that each of these components has to communicate, right? And for communication, these services have to be discovered. There is so what they've come up with now is a new way of identifying which services are active, and the way in which they are identified, what the service allows and what it can do. So there's a master service which runs, which talks to all of these services, and that's how you can communicate with your robot. Cool. So this is about ROS. So anyone interested in robotics must look into ROS, and it is what you'll probably find in the company that you end up working for. Coming up is a very big problem with robotics, which is generalization or specialization. Now, if you talk about robotics, what you will generally observe is that either the robots are doing something very, very specific. For example, in industrial robots, you will have them doing only a particular thing. Like, for example, it might be picking up an object and placing it somewhere. So it will keep on doing only that task. And that is simpler to create. What is difficult is that for the consumer market, you want to create a generalized robot. Now, here what you can see is grasp pose detection. Now, as we talked about this before, picking up an object is a very simple task for a human being. However, for a robot, he needs to have an exact number of steps which the robot will take in order to pick the object up. And that is a difficult problem to solve because the objects can vary in size, which would mean the algorithm will have to give a different value to the motors every time. How many degrees should it open by? How much pressure should it apply to pick up the object firmly? So all of these things are very, very difficult to do. That is, generalization is difficult. The reason why it's difficult is because we write algorithms in a deterministic fashion. The real world is non-deterministic. And this is very relevant in case of robots where they have no idea what environment they're going to be in or what values the sensor might give them. And we use deterministic math to write those algorithms. So we have got deterministic algorithms based on deterministic math, but we are putting these robots and algorithms in non-deterministic conditions. And the end result is that we get non-deterministic nature of robots, where we are not able to specifically say what the robot can or cannot do. Now, this is slowly starting to change. With AI and specifically machine learning and deep learning, we can now create more general models for the robots such that they can pick up, like for example, this grasp pose detection, GPD algorithm. So this GPD is using machine learning to estimate how much it needs to open the claw by and at what point should it try to grab the particular object. So why is this so difficult before machine learning is because you cannot keep writing deterministic algorithms. Imagine you are working at NASA, you are creating a rover sitting on Earth, which is going to go to a planet like Mars, where the environment is not known, and you are trying to write a deterministic program for it. It is almost impossible to do it without all of these new techniques that we have. So generalization in robotics has now been enabled by machine learning and AI techniques. And now we have come to a point where the algorithms are getting better and better, and they can do more of these generalized tasks. Now, even in case of simulators, you might simulate in one environment or two environments. But at the end of the day, your algorithm needs to work for any environment. And that's the kind of challenge that robotics faces today, where you need to create generalized algorithms which can work or find a path in no matter what condition they are put in. So AI and ML have got a huge have been a huge boon for the robotics field, and it's going to continue to grow from here. It's a fun fact for you that Mars has become the second planet with more computers running Linux than Windows. So you will find Linux computers very often on Earth, because most of the servers are Linux, Android phones are Linux, so routers are Linux. We talked about how IoT is Linux. So you will find a lot of them running Linux here than Windows. And on Mars, we now have the Curiosity rover, the Perseverance rover, all of them are running Linux. So it's a derivative of ROS, and NASA has its own custom software around it. It's all open source, by the way, so you can go ahead and look it up. So I think that's all I have from a robotics point of view. Let me check the questions for robotics. So I'll give you like around 5 minutes, so you can give me questions on robotics. Can we look at robotics as a lucrative career option in India? Because it appears like in India there is no innovation as such in this field. Not true. So I will not call it a lucrative career option, because it's a high skill kind of a job. So if you're really good, then your hireability is going to be there, because there is so the DRDO, ISRO, these agencies in India, they are heavily investing in autonomous or semi-autonomous robots. Then there are industrial robotics companies which are there, and they are making many different kinds of robots for industries. There are companies which are making consumer level robotics like Roomba and etc., which you guys have seen, which go around cleaning the house, and some others. So these three fields. So which ones? The first is DRDO and ISRO. The second is industrial IoT robotics, and the third is consumer level robotics. So in India, these three things are happening. The problem is that this simulator part just happened right now. Before this, there was not enough funding which the universities, etc., were getting in order to develop robotics fast enough. Now, DRDO and ISRO are heavily funded organizations, and those have the tools and the ability to make and innovate in the field of robotics. But now with simulators and the overall reduction in costs, you will see a lot more happening in robotics. So yes, it's going to be a very exciting career or a lucrative career option in the coming years. But as I said, you'll have to be good with at least 2 branches of engineering. And the field is difficult. It is highly skilled. It is not as simple as your average developer job, which you will probably get in a company after your engineering ends. So it is a specific job. It's highly skilled, and there's not enough penetration, as you rightly claimed, in the market. But it's going to be big. That's for sure. Waiting on more questions. Even if you have missed out any IoT question, you can always send it. As for starters, as engineering students, how do we start learning basic robotics? That's a great question, and it's a question which I myself pondered over for a while. What is the best starting point for robotics? So initially, what you want is you want to start off with building a basic robo to give you an idea of the electronics and the mechanical aspect of it. Now, when I said basic robo, this does not mean that it is going to be autonomous. What it means is it's a remote controlled mechanical device which can move around. You start off with that. So there are kits which are available online. I can show it to you if you want. They are very cheaply available. They come with 2 wheels, motors for both of them, and they come with the chip itself and the housing for this. And you can build this robo by yourself, and you can create an app for it which controls the robo over Bluetooth or over Wi-Fi. That is from the web browser. You can control it. You can add a camera to it, and then slowly you build on top of it. So first stage is that you make a remote controlled, completely manual robo. Then you slowly go ahead and you add electronics to it. For example, you will add an ultrasonic sensor. Then you will add logic, which will make the robo stop when the ultrasonic sensor senses something in a particular thing. Then you will add a camera to it. Then you will allow it to navigate itself. So this is how you build on top of it. Now, if you have constraints on how much of these physical hardware kits that you can purchase, then as I said, simulators are available today, and you can get tutorials online. There is a very good simulator named Gazebo. There are other simulators which are available. There is Carla for self-driving cars. So if you can buy hardware, buy cheap hardware and start off with it. So you get a feel of how the electronics work and how the mechanical aspects of robotics work. And once you are slightly more familiar with this idea, then you can try to build your own robo or write your own algorithms for it. If not, if you cannot buy hardware, if you're not in a position to purchase hardware for it, you can go ahead and use simulators. You can also write a purely software-oriented experience. So for example, you might not want to build the robo at all. You are just interested in writing a better path-finding algorithm. You can totally do that with ROS and simulators. So you can just concentrate on writing the algorithm if you want to do that. So the idea is that you can concentrate on any one aspect of robotics and you can start off from there. So that's, hopefully that answers your question. If not, you can just say. Autonomous vehicles have started to come out in India, but they are not 100% safe. Do you think it is possible to have autonomous vehicles on unpredictable roads of India? Okay, so just for additional context and general knowledge, autonomous vehicles have been banned in India. Basically, self-driving cars have been banned in India by the government. The reason for that is that there is no framework that we have right now for the safety aspects of it. Other countries which have approved them in the past, they are now facing the legal and ethical challenge of figuring out what to do in cases where a person is hit by an autonomous vehicle. Who is to blame? Is the programmer to blame? Is the company to blame? Is the software to blame? And who is held accountable? So there are many ethics-related questions which are being raised. And India as a market is not ready for self-driving cars. Yes, Tesla is coming out in India soon. They are going to have a manufacturing plant here. The point is that they will not be enabling the self-driving aspect of it. What you will find, so there are levels in self-driving cars. There's level 4 autonomy, level 3, etc. Now, what you will find is that these cars will be able to slowly start parking themselves, which is what you will see first, because the space is controlled and there is not enough speed to actually hit someone. Then you will, second thing that you will see is the Tesla summon feature, wherein you are in a parking lot, you will stand outside the parking lot and you summon the car. So the car slowly moves out of where it currently is and it comes to you. Then you will start seeing what is called adaptive cruise control, which is basically, if you're on a highway, you can put it in adaptive cruise control mode and it will steer to keep you in lane. Now in the US, these things are very simple to do because the roads will always be uniform. There will always be markings on the road. There will be signboards which say the top speed at every point, like every few kilometers, miles. But in India, we cannot take any of those things for granted. But you will still get autonomous cruise control, which will steer to keep you in lane. Second, it will brake you automatically if you are very close to the vehicle in front, and it will try to jolt you awake if you end up falling asleep on the wheel. However, all these three will have user supervision at a very high rate. For example, if it is adaptive cruise control and if you take your hand off the steering wheel, the adaptive cruise control will disengage and you will have to steer the car. And the car will jolt you by braking to make you understand that it is no longer driving on its own. Over time, yes, self-driving will happen, but even if it's the US, even if it's India, it's going to be much farther off. The other problem with that is, apart from the Tesla, very few other vehicles have the ability to receive updates and make the self-driving tech better. So the thing is that you will not see the user adoption for self-driving at a scale which will allow them to progress as quickly. What you will, however, see is for things like semi-trucks or these large vehicles, which are typically only operating at night and going very long distances on the highway, those will be the first which actually end up getting automated, rather than the consumer-facing cars which you and I today use. And that's how I see the landscape becoming. But as you have rightly claimed, unpredictable roads of India is a huge problem, because we talked about this before. You have deterministic algorithms working in undeterministic conditions. And in India, the undeterministic conditions are so vast that writing something that which can generalize it is an impossible task in itself. But as I said, you will get these levels of autonomy slowly, and semi-trucks and trucks in general will be the first to get automated. So I think that's, and by the time they progress, we will have some kind of a legal framework which can decide what are the minimum requirements for a car to be called level 2 autonomous, level 3 autonomous, what are the laws which they must comply with, what are the safety parameters, what will ARAI have to test, what does it need to pass. These things will progress over time. But it's slow moving in India because we don't have very good regulations framework. Even something like Bitcoin or cryptocurrencies in general have not been regularized yet. So it takes time. So I think this is going to be a long wait. Any more questions? One interesting aspect of autonomous vehicles is that the more number of autonomous vehicles you have, the safer it becomes. So that is something which is going to be another problem in India, wherein the adoption rate is going to be so slow because people are still using manual cars which are BS2, BS3 today. And people are, so now we have got a scrappage policy and etc. But people have been reluctant to change cars in India overall. With self-driving cars or autonomous vehicles, if all the other drivers are manual, as in they're physically driving the car, the self-driving ones are in a greater problem. You get my point, that if more number of autonomous vehicles are on the road, it is safer for everyone. But the moment you have more manual drivers, they are going to try and supersede the autonomous vehicle or make some kind of moves which are unpredictable. If everything is a computer-based system, then you can have predictability in the system. But if you have got everything else which is unpredictable and one predictable aspect, then it's going to be very, very tough. So this is another side point, I feel, which is going to keep the innovation at a slower pace here. So any more questions, guys? I think we've got around a few minutes. So like a wrap up question or something? Anything?
I guess that's it for the questions, sir.
Cool.
Um, so I express my sincere thanks to Mr. Dhaval Gujar for taking out his time to enlighten us all and clear our doubts. Thank you, sir. So this session is a part of AccessDenied'21. So AccessDenied is a 36-hour hackathon conducted by IETE ISF from 19th March to 21st March. There are exciting crash prizes awaiting. The winner gets 20,000 rupees, the runner-up gets 15,000, and the second runner-up gets 10,000 rupees. There are also track-specific prizes and other special mention prizes along with it. We will also be having similar sessions from prominent speakers throughout this week as part of the hackathon. Access Denied is one of the best hackathons conducted in VIT. If you haven't registered yet, then you can click on the link in descriptions to register. I once again thank Mr. Dhaval Gujar for enlightening us on this topic. Thank you, sir. Thank you, everyone.